at its heart. Okay, so we'll see a bit of that. And the other areas in which you might encounter is, for instance, driving in traffic. Right? So this, I'm sure all of you have observed. So you might want to like slightly optimize your path so that you maybe get to a better thing and so on. Okay. And actually, at the larger scale, this happens in network routing. So you try to see if there are shorter paths and take that, things like this. So yeah, but more generally, whenever you have a search problem which is kind of unstructured, so it turns out local search is probably a reasonable thing to try. Okay, so you start with some solution and you try to move around, see if you can improve it. Okay, so yeah, so we'll see this example of non-convex optimization in a little bit. Okay, so far I haven't defined what local search is. So let's give a concrete example. Okay, and before going there, so this is one thing that you should remember. So you should, roughly speaking, when does local search work? It works when somehow the local optimum is typically roughly equal to the global optimum. Okay, so if you are stuck somewhere, you can't improve your path much, or you can't improve your solution much, then it should somehow mean that you are close to the global optimum. Okay, so only in such cases, or if you can prove a statement of this kind, you can show that, then you can conclude that local search is useful. And some problems in which this holds, and some problems for which this does not hold. Okay, so we'll see examples of both. So I wanted to illustrate using a very simple example. So this is very similar, very reminiscent of the matching problem we saw last time. But here this is a bipartite graph. Okay, so this is, imagine someone who wants to distribute n gifts to n children. And suppose you have a happiness value for every gift. Okay, so for if child I is given gift j, okay, so let's write all the children on the left and gifts. So you have 1 through n, you have 1 through n. Okay, so if child I is given gift j, then the happiness that he or she obtains from it is aij. Okay, so that's the weight on this. Values for different children. Okay, so that's how I've formulated the problem. And what is the goal? So this is so Santa Claus here just wants to optimize the total value. Okay, so he doesn't care about each individual child and so on. So suppose our goal is to maximize total happiness. Okay, so you want to find an assignment of gifts. So let's call this assignment. So assignment is basically a function, right? So let's denote this by f that maps n to n. What is that parenthesis n? Everybody know? Okay, so if I write notation like this, I might do it inadvertently. If you don't understand, please ask. So what is
integer to integer switch?
Yeah, so this usually refers to integers, the set 1 through n. Okay, 1, 2, 3, n. So this is standard notation usually, and so we are saying f is a function that maps numbers from 1 to n to numbers from 1 to n. Okay, so it's basically, we want it also to be a permutation because you don't want one child receiving 2 gifts, right? So every gift maps to so it's like gift j goes to child f of j. Okay, I'm just introducing some notation so that I can write down the optimization. So this is what we want to find. So we want to find an assignment. Okay, and the objective function is sum over j a f of j. Okay, so this is just notation. So if you think of it as a graph, then what I want you to find is matching where every gift goes to precisely one child, such that the sum of the edge weights of the edges you chose is as large as possible. Okay. So yeah, I'll pause here so that you guys digest the notation. Any questions on the problem? Alright, so how would you solve this problem? Suppose your goal is to maximize the total happiness. So any ideas? Like every child has different value for each gift, right? So that's the main thing. Oh, so okay, so I just wanted to mention that this problem is called weighted bipartite matching. This is used in a lot of places. It's like matching people to jobs, like dating websites, things like this. Okay, so also advertising, matching pages to advertising. That's the other important place people use it. Yeah.
You could do a greedy approach. Just take the highest A and then remove both nodes. So remove the child and the gift.
Okay, so I was anticipating this. That's why I have a slide with greedy algorithm. Okay, so what you would try is that, okay, so I have this graph between children and gifts. Right? So you could say, okay, I pick the gift that has the maximum value for any child. Okay, so the maximum of the entry in this matrix. You could say I assign this to this and continue this way. Okay, so eventually you might get stuck, in which case you always look among the leftover ones. Okay, so at every point you will have some portion of the matrix left. Okay. So once I assign this gift j to some child, then the whole row of this matrix is gone. Okay, so if you think of it as a matrix, so this I've written it as A. So the entire row of this matrix is gone. Row, column perhaps. Yeah, actually the column. The entire column is gone because gift j has been assigned. Okay. So and then you keep doing the rest of it. So this is one greedy algorithm. Any other greedy algorithm to think of? I mean, do you expect this to produce the right answer? No, right? So greedy almost, that's the rule of thumb. Unless you're very lucky, greedy doesn't give you good answer.
Search pairs of edges for trades to improve the total.
Yeah, so we'll see that. That's local search again. Okay, so I mean that's what I will call local search. Yeah. So, but we'll come to that in a bit. So, any other algorithm? So another very similar thing could be go through the gifts one by one and keep assigning a gift to the largest, the child that values it the most, okay, among the children that are left. So that's other obvious greedy algorithm. So this is the other algorithm, and this also you can show doesn't really work. Okay, so there's examples in which this can be really bad. Okay, so alright, so what's the solution? So I want to suggest a local solution, a local search type algorithm. Okay, so because that's what we want to try. So we're going to look at a suggestion that he made. Okay, so let's start with some solution and try to see if you can improve it. Okay, so what does it mean? So what it means is, let's say you start with some assignment, like you assign. I'm going to take a simple example with let's say 5 kids. One. Maybe this is your current solution. Okay, so gift 1 you assign to child 2, 2 to 1 and so on. So note that any assignment looks like this, it's essentially a matching in the bipartite graph. So now, what could be an obvious way to improve such a matching? Like this is the current assignment that you've made. Suppose I were to tell you, oh, see if you can improve this a little bit. Then what would you try doing? Okay, maybe that's, yeah.
Maybe just compare pairs.
What do you mean?
See if each of them has the optimal solution. If they're not, you can swap them, kind of like a sorting.
So you want to, but pair of what? Pair of what?
Pair of children, pair of edges.
Okay, so you're looking at this edge and let's say this edge. Okay. And you want to see if assigning 1 to this child and 4 to this child is better. Okay. So is the algorithm clear? So is that what you were also going to suggest?
No, I wanted to basically do a divide thing.
Okay.
Divide the nodes. First assign locally in each division the best gift for each child, and
Okay.
then try to concatenate divisions basically, and then see if our assignment is proper in that division.
Yeah, so that's fine, but that's an algorithm from scratch, right? So in some sense, you are saying you're giving an alternate algorithm for doing this, for doing the problem. So what I was asking for is something where you have a solution and you just want to see if you can improve it. Okay, so that's the key thing in local search, that you don't want to like build a solution from scratch using. I mean, that's also a perfectly fine way to solve the problem from scratch. Okay, but we are looking at algorithms where you just have some solution, try to improve it. And what he suggested is something where you had a solution and you look at any 2 edges in the solution, try to see if swapping them helps. Okay, so let's try to go with that. Okay, so yeah.
The start is using greedy or is random?
It could be anything actually.
Does
But in
not-
practice, you might want to start with something where you hope that you have a reasonable start.
Then
Like greedy or something.
we start greedy and we
Yeah. Although the argument I will make will hold for any start. Okay. So, yeah, well, that's a good point. Yeah, so very often this happens a lot in machine learning. You use some heuristics to actually come up with a good initializer, and that's actually usually it's very important to have a decent initializer. Okay, so that's why that's a very good point. So okay, so the algorithm is just pick any, I mean, or rather for every pair. Okay, let me start to see if I can do easier. So for every pair of edges in the current solution, check if swapping the gifts. I haven't defined what swapping is, but essentially this is what it is. You take these 2 and assign gift 4 to child 2 and assign gift 1 to child 3. So if these were the 2 edges. And check if swapping improves the solution. Okay. So, and if so, just go ahead and swap. Okay, if so, just go ahead and swap. And otherwise, just halt. So if so, swap. And we don't care so much about which ones you swap. Although in practice you might want to make the swap that actually gives you the most benefit. Okay. So at this point I don't care much about what you swap. And else, just return current solution. Okay, so swap and repeat. So go back to this step. Okay, otherwise, you just return the current solution. So is the algorithm clear? So this is a prototypical example of local search. Okay, so start with some solution, see if you can make some minor tweaks to it, see if it improves the solution. If so, keep improving it, keep doing this process. Otherwise, just stop and return. So what do you guys think? Does this return an optimal solution? Okay. Why not?
You could get to a spot where no swaps improve it, but if you make like 2 swaps in a row, then it might improve it. So it would stop.
Can you give an example of that?
Like if 2, in this case, if 2 and 3 would be better, but in order to connect those, you'd have to swap. So child 2 and gift 3. In order to connect those, you have to swap 2 with child 4 and then do another swap to get it to 3.
Yeah, so you're right. I mean, I don't know if this particular example actually works out, but you can actually construct examples where this is actually not optimal. Yeah.
Because there will be some kind of loop that contains more than 2 edges. I can give an example.
What do you mean a loop that contains more than 2 edges?
I can give an example. So
Uh-huh.
suppose there are 3 children and 3 gifts,
Yeah.
and then one possible solution would be the first one the first gift to the first child, and the second to the second, and the third to the third.
Okay.
And another solution would be the first to the second, and the second to the third, and
Yeah.
the third to one. In this case, you cannot just swap any 2, but you can try two groups of choice. One is how if 1 to 1, 2 to 2, 3 to 3, or 1 to 2, 2 to 3, 3 to 1. This is 2 sets of edges, and you cannot just swap them.
Okay, but what you're suggesting seems to say that it can be actually arbitrarily far off, right? Because, I mean, if what you're saying is correct, then one should be able to say that, okay, so suppose I put weights of 1 on these edges and weights of 10 on these edges, on the edges in this other matching, then this is 10 times worse than the other.
You can just assign each edge as 1, and the only edge back from 3 to 1 as 100.
Okay, so all edges are 1 except one of them which is 100. 3 to 1. Is that what you're saying?
I'm not so sure.
Okay, so you'll realize this also doesn't work. Okay, so you can't make this very bad, and that's what we are going to show actually. But you can make it a little bit bad. So you can, so this, I mean, I don't want to go into this too much because I want to make this a homework problem. But you can always come up with a solution where, I mean, you can come up with instances where this is actually a factor 2 away from optimal. Okay? And now we are going to show that factor 2 is like the best possible. Okay, so in some sense, so the claim today is that this is the worst you can get. Okay, so solution obtained like this. LS is local search, is is at least half the optimal cost. Okay. So remember our goal is, okay, I shouldn't maybe call it cost because this is the happiness value, this is something you want to maximize. Yeah.
So does that mean if we checked like every permutation of 3 instead of just 2, we could get 1/3 or 2/3?
That's also going to be a homework. Yeah. But you're right. So this is, I want to come to this actually, this is a great point. So what he's trying to ask is, suppose instead of checking every pair of edges, check every triple of edges. Okay? And you try to see if changing the mapping between those 3 actually improves the solution. Okay? Then you can actually show that this, that you can get a better theorem where you actually get it's at least 2/3 of the optimum. Okay? And if you check four of them at a time, then you get 3/4 and so on. Okay? So the caveat here is that if you've got to check every pair or every triple of edges, then you're going to take time roughly n cubed. You know, if you want to check every four of them, then you take time n to the 4. Okay? So this is one of these simple instances where there's a trade-off between the running time and the approximation factor you get. Okay? So this is rarely happens in algorithms, but when it does, it's nice. Okay, so
And would it be a mapping, would it be an improvement if we have 1 to 2 and if we are just comparing 1 to 1, 1 to 3, 1 to 4, 1 to 5 and see which one is the maximum and we take.
but that's going back to the greedy world, right? So in which case we know you can be quite bad actually, you can be utterly bad. So that will not end up working. That you can't even get a 2-factor, turns out. Okay. So yeah, basically because you start with 1. Basically makes a mistake. All right, so okay, so let's see how you show this, right? So the 2/3 you're going to show in the homework, but let's see how you show the factor 2, 1/2. So how would you go about starting to prove this? I mean, we want to show that whatever this thing outputs is at least half of what the optimum is. Any guesses? Yeah. So again, this is kind of reminiscent of what we did last time with matching. Okay, so in that sense, so some of the idea. How did we proceed there?
Yeah. So going from last time, we know that if we're going to be doing swaps, there's at least one other adjacent neighbor per se that we can do that swap with. And if we do that swap, we don't want to swap it anymore per se because we've already gone through that list. And we know that you're going to go through that half at the time.
Right. But how does?
Probably showing that later.
Yeah. Okay. So yeah, if you maybe you should expand on that. So what was what was the first step, right? So you want to compare whatever you have with the optimum solution. Okay. So what so how would you go about reasoning about something like this? Does that make sense?
Finding the optimal solution.
Sorry?
Finding the optimal solution first.
Well, we can't find the optimal solution, right? Or rather, I haven't told you how to find the optimal solution yet. So this is typically the problem. I mean, in this case, there is another algorithm to actually find an optimal solution, but very often you can make arguments like this for NP-hard problems, where you can't actually find the optimal solution. But you can always assume, okay, I don't know what it is, but let the optimum be something. Try to reason with respect to that optimum. Okay. So that's the way we usually go about in approximations, when proving approximation factors. You say that, okay, I don't know what the optimum is, but let me not care, but I'm going to assume it is something, and prove that my algorithm has cost at least half of that. Okay. So that will be the starting point. Okay, so let F be the optimal assignment. So recall F is the function that maps 1 to n to 1. And so there's just one. Okay, so the optimal solution maps I to f of I. So now, how do I reason about my solutions? Okay, so now I have some mapping, right? It looks like this, and I know that it's locally optimal. Okay, so there's no swap such that things get better. Okay, so does that make sense? So assume this is a solution. Let's call this G or something. This is a solution where local search ended. Okay, which means that there's no local improvement you can do to improve your solution. So now can you say something? Yeah.
The sum of the two edges that are connecting those two has to be greater than that edge by itself. So there, each of those in the solution is found for it looks like O and I can't quite read it, or I and F of I.
Yeah.
Have to be on other edges themselves, and the sum of those two has to be greater than that edge, or would have made that swap just to get that optimal edge.
Okay, so you're assuming everything is non-negative, which is fine, right? So we need to assume all the AIs are non-negative, but yeah, I forgot to mention that. Okay, so all right. So what he's saying is, let's look at some edge in the optimal solution. Now here I was being mapped to Fi. So we know that in our solution G, so you would have, I mean, if you assigned I to f of I, then you're fine. Okay, then you've kind of done well for yourself. Then you can in some sense remove I and f of I from the problem and work just with the smaller problem. Okay, so that one is true. But otherwise you applied, I mean otherwise you assigned I to somebody else. Okay. So I was assigned to somebody else, and child f of I was assigned some gift. Right, so child f of I was assigned some gift. Okay. Let's call this, okay, actually maybe I should point to that picture. So I was assigned to 2 and so this is in that picture. Okay, maybe I should draw dots here. Okay. This is also dotted. Okay. So yeah. So this I was assigned somebody, and this f of I was assigned somebody else's gift. Okay. So now what he's saying is that the cost of these two edges better be at least this edge. Okay. So to write it formally, so what you have is that a g of I. Okay, that's I was assigned to g of I in our local search optimum plus a. Let's suppose j was assigned to f of I. So a j g of j. Okay. So g of j is f of I. So it's the same. Is bigger than or equal to a f of I. So this is what it is. right? So you know that these two edges are at least as big as this edge. And the reason, and why is this true? Anybody else?
So the ones that we would have made a swap, yeah.
Yeah, so if this wasn't true, you would have just, I mean, you can pick these two edges, you would have swapped the endpoints. So you would have mapped I to f of I and j to that 2. Okay. And so you know that all the weights are non-negative, therefore the cost will only be bigger. Okay, so do you all see this reasoning? So it's important that you understand this because this is typical of all of most local search arguments. That you say that if you are locally optimum, then some condition can be deduced from that fact, the fact that you are locally optimum, and that can be used to show that your solution is good enough.
So when the two values equal, will you do the exchange?
Sorry?
If the left equals
Yeah.
the right,
Yeah.
will you do the exchange?
Yeah, so when you do the, you mean, oh, if, no, you don't do the exchange, but that's why I said you always have this to be bigger than or equal to that.
But isn't there supposed to be another term after that? Because two edges, sum of two edges greater than sum of two other edges.
Yes, in fact, it's also bigger than or equal to this plus something else.
So
That something else is always bigger than or equal to 0. Therefore, it's bigger than equal. Yeah.
So, if we ensure this at every level and we join this cross edge, if we don't find this condition, then
Okay.
what will happen?
What is a level now?
We find this for both the edges, like edge numbers first and second. We will find if their individual edge is greater than the cross edge. Okay, and if we don't find that to be the case and we just add the cross edge, what will happen to the other node?
No, so what you will actually do is add this edge and that. Okay, so you'll add I f of I and so you'll add both the cross edges, right? So you have these two, okay, and you will try to see if swapping this one with this one is better, right? And you know that because local search ended, AGI plus this is bigger than or equal to that edge plus that edge, both the sum of the two cross edges.
So this just assume that we will just match every child to the node that is corresponding to the next, like level wise. We will just match level wise, and then if the cross edge gives us a better solution, then we will swap. We will perform the cross edge connection.
Yeah, but there's no notion of level here. I mean, it doesn't have to be that I is mapped to I, right? So this is just for convenience that I drew the picture like this. It could be that the G matching looked something like this. Okay, so G matching could look like this, and now I will try to see if this assignment is better. Okay, so that's, yeah.
So F is the optimal assignment, and
Yes.
we are trying to maximize happiness. Right?
Yes.
So then we would obviously want to swap and get this value. Why would F be the... So if GI plus GJ is greater than this, then how is this the optimal value?
That's the point. Yeah, that's the proof. I mean that. So if you had, if G of I plus J of this is strictly less than that, then you would have enough swapping. Is that what you're saying?
I mean, yours...
No, I mean this could totally be true, right? I mean there's only one edge on the right, so there's only one edge cost on the right. So here there are two edges.
So like, why is this true? Because if this...
Yeah. Okay. So let's see, right? So I want to claim that this is true. Okay. And the reason is, suppose this were not. Okay. Suppose this is not true. Then A G of I plus this thing is strictly less than the right hand.
Yeah.
In which case, doing the swap, okay, with G gives me a better solution. So local search could not have ended with G. Okay. I'm not saying anything about F here. I'm just saying that if this inequality were not true,
Yeah.
okay, then local search could not have ended with G. Okay, so let me write that down so that it's clear to everybody. So the proof of that smaller claim is that if J is less than I, then local search with G. Okay, so this is all I'm saying. I'm just saying that local search could not have ended with G. Not saying anything about F.
So my local search ended with G,
Yeah.
but the optimal is F.
Yeah.
So like for at least these two pairs, my local is better than the optimal.
No, so you are only looking at one edge of the optimum. See, these are actually, this is the happiness that only this f of I is getting in the optimum. While on the left side you have happiness that G was giving to 2 plus the happiness that G was giving to f of I. So there's a sum of two happinesses.
This is also greater than F of Fi plus another term, right?
Yeah, but that other term is not an f. So the other term is f of, is A of J here and 2 on the left, right? So yeah, and this need not, J need not have been mapped to 2 by F inequality. Okay, so we must have this part. Okay, so what does that give, right? So we have this, and we have this for every I. Okay, so for every I, we have that J is bigger than or equal to A f of I. So this is already starting to look promising, right? So you have a couple of G's on the left, G I's on the left, and some Fi I's on the right. Right? Because what do we eventually want to show? We want to eventually, our goal is to show that the optimas are not, so we want to show that sum over I, A, G of I is at least half of sum over I, A, F of I. Okay. So this was our goal to start with. This is the happiness value for the optimum, this is the happiness value for your solution. So
max of 2, right?
Sorry?
So we take max of the 2 and then we say that that is 2 into, at most 2 into max of that.
You could do that, but two different I's could end up with the same max. So but what is even more natural than that? I mean, you have that inequality, what would you do to get something like this? Yeah.
What if we consider the worst case where G gets none of the edges correct?
Okay.
And then we could, so we'd have n of these terms and we'd sum them up. And would that give us the equation we're looking for?
Yeah, so what you've got to do is just sum this equation over all I. Right? So you have this kind of an equation for every particular I. Okay? And so there's a little bit of argument to make here, which is that every term on the left appears precisely twice. And that you can verify by saying that I get one term, okay, I get one term for somebody mapping into f of I, get one term for somebody mapping out of I. Okay, so yeah, let me write it down. Yeah. So what does this mean? So we could write it as A f of I. Let me write it in the other way around because that is that. A is less than or equal to A. Okay. So I get one term corresponding to somebody who is mapping into f of I, right? Via G. So that, just to be consistent, I will write it as f of I and G inverse of f of I. Okay, so this is messy notation, but this will, you will see intuitively why this is going on. Okay, so, and then the other term, that was the J there. And the other term is somebody who maps out of I.
G inverse Ji and J.
Yeah. So plus somebody who maps out of I, right? So this is just a G of I. Okay. So I've written, the reason I wrote this equation like this is because I want everything in terms of I. Okay, so there I assumed G inverse of f of I is J, just so that I could, I could explain better. But now I'm just writing it out because I need to do the computation. Okay, so yeah.
Why is G inverse of f of I equal to G J J?
Oh, I just, so earlier, how did I define J, right? I defined J as the thing that that G maps to f of I. Okay, that's like saying it's G inverse. So if you take G of that, it's just okay. So I just defined J that way earlier just so that I could explain what that means. Explain this word. Alright, so this is what we have. And now if I sum this equation, okay, so sum over I here, sum over I here of the whole thing. Okay. So the second term is the kind that we want. So the second term is precisely the left side of over there. Okay, and this guy is basically this term. Okay, so this is this. Okay, and if I break this sum as two summations, then this part corresponds to this. Okay. Now, what about this part? This looks messy, but is it actually messy? What is this trying to do? So this is summing, now you are summing over the left sides, and you are summing for everything over here, you are summing the G value, or rather the H value that, like suppose G was mapping J to this, then you are summing this H value, right? So what is this summation again?
The sum of all happiness.
But for what function? For G, right? Intuitively to me it's very clear, but if it's not, I can try to. So basically, for everything on the left, you are looking at the inverse in G, and you are mapping, and you are adding this value. Okay? So it's just like summing over the right-hand side of I G of I. So that's why you get that both these terms, the summation of both these terms are actually equal. Okay? This summation equal to the summation of that. And that's equal to 2 times sum over I, A, G of I. And now if you just take the half to that side, you get what you want. Okay, because this is what we wanted to show. And I got that this term versus this. I observed that this is equal to that, so it's 2 times that. And so you get that that is at least half of it.
So when you say H values, you mean the happiness value, right?
Yes. Yeah.
Like
The happiness that
maps the right to the left.
no happiness that this vertex gets from J. Okay. So yeah, this is actually intuitively a simple argument. It's just notation heavy, so that's why it might take a second or so to realize. Any other questions? Alright, so this is what it is. Okay, so what we've shown is that if you have a solution obtained from local search and it has happiness, then it has happiness at least half the option. This is how you work. Okay, good. So this this is one example where local search gives a reasonable answer. There's actually another example which we might or might not see the local search variant of it, but it turns out to be true. Okay, so when we study spanning trees next week, okay, so here the problem is that you have a graph and you want to construct pick a subset of edges such that E prime spans the entire graph. Okay, this is an undirected graph. Okay, so what we mean by this is that it connects every pair of vertices. Connects every pair. Okay, and there's also edge weights with edge weights. Connects every pair, and sum of weights of edges in E prime is minimized. Okay, so this is what is called the minimum spanning tree problem. So you have a graph, and the standard motivation for this is think of your graph as a network, okay, as like a communication network or something, where, or rather, maybe a road network might be also a decent example, and the edge weight corresponds to the cost of laying this road. So this is for WE corresponds to the cost of laying this road. Now you want to connect everybody, and there's many ways you can connect everybody, okay, and you want to find the one that connects it with the least possible total cost. So that's one standard motivation for minimum spanning tree. Okay, so anyone here who has not seen minimum spanning tree before? Oh, okay. So we'll spend more time on this next week. So right now it's not that important that you understand what's going on here, but do take a look back at this slide next week. Okay. So that's that's all I was saying. But now I want to say that this is one of the other problems where local search actually finds an optimal solution. And the reason I'm mentioning this is because in this case, what is local search? So you have one tree and you want to get to a different tree. So this is often something you've got to think about if you are thinking of local search algorithms, which is what do I mean by locally improving? Okay. So in some problems, like in this matching type problem, local improvement was clear, right? You try to see if there are two edges that can swap. But if you have a spanning tree, then you've got some tree. Let's say I have, okay, so let's say I have this, this. Okay. So this is one tree, right? So it's think of it as, I mean, it connects every vertex to every other vertex, and and etc. Okay, so what does it mean to move from to improve this tree? Could you think of a natural way?
And I pick up an edge.
Sorry?
I pick up an edge.
Okay.
Between E and V.
Between
Or
what?
between X and Y.
Okay. Between one vertex and any other vertex.
And then I pick up another node Z, and I say if the distance, the weight between X and Z plus Z and Y is less than the edge that I picked up. Am I explaining?
Yeah. So let's see. Okay. So you're saying that let's not call it epsilon. Let's call it x and y. Okay.
X and
yeah.
X and Y, and then I pick Z.
Yeah, so Z is somebody else. But do you want it to be this one or do you want it to be somebody else?
Z is another one.
Okay, so it's somebody else, okay.
If the distance between X and Z plus Z and Y is less than the distance between X and Y.
Okay.
And
Then we will add it.
And then I swap.
Yeah, so something like this you can actually do, but the distance is
The
a...
weight.
Well, I mean, this is not a complete graph, right? So there need not, if I pick Z to be somebody else, then there need not be an edge like this. So that's one of the issues. But you could always say this is a connected graph, so there is a path. I mean, so the set of edges I have chosen so far is a path. So you could try swapping that. That's roughly the idea actually, but yeah, maybe you raise it. Yeah.
For a tree, every time you add one more edge, there will be a circle. And each time pick an unused edge and then try to add it to the tree. And then for the circle, remove the edge with the maximum width.
Okay, so have you seen this before? Oh, okay. Yeah, so it's very perfect. Yeah.
So suppose we take one node and we take the rest of the graph as a black box.
Okay.
And now we say that from that graph there is an edge connecting to the graph to that node.
Okay.
Now we take that and then we take another node
Yeah.
which is not connected to that node from the graph.
Yeah.
And then we consider this node, this edge and that edge. And if the new edge has a greater width, we just swap.
So you're basically saying I look at, I mean, I think what you're saying ultimately amounts to what she said, which is that basically look at any edge that's not in the graph already, okay, that's not in the tree already, okay. So suppose I add that edge to the tree, okay? Then in the tree there would have been a path that went from here to here, because the tree actually connected every vertex to every other vertex. Okay, so in the tree there would have been a path that went from, so your vertex was V, and I added, let's say, an edge that went to some U. There would have been some path from U to V in the tree itself. Now I can go through this path, and I can try to remove one of the edges along this path and actually add this edge instead. Now the tree remains connected. I mean, what you get is still a connected graph, because you've broken this bridge, okay, but now you can get from this vertex to that just using the whole side. So everybody is still connected. So this is why everybody is still connected, and you still, and this could potentially have a smaller cost, because if this edge weight was smaller than this edge weight, then this swap actually made sense. And this is exactly what she's saying, right? So that add an edge, try to see if you can remove a larger edge along the path. So that's one way of getting from one spanning tree to a different spanning tree. So note what I have done, right? So I have actually argued that the next thing that you get is also a spanning tree. Okay, so that's something you need to do. And that's it. Okay, so it turns out this algorithm actually produces the optimum spanning trees. So produces minimum spanning tree. So before I go to this, I want to mention one thing about using local search for especially combinatorial type algorithms like the ones that we've seen so far, which is the running time. Yeah, I forgot to have it on the slide, I just remembered. So, what do you guys think about the running time of local search? Okay, because we are just doing swaps, right? We're doing swaps as long as things improve. Okay, so is this efficient? I mean, it's clear from all these examples that every iteration is efficient, it's reasonably efficient, right? Because you try to add an edge, you try to do a swap. So every iteration is pretty efficient. But what about the overall thing? Is
N
it,
squared.
sorry?
N squared.
Why?
NC2 because you can choose an edge that can get most NC2 edges which amounts to N squared.
Right, but you can add an edge, remove it, keep adding and so on.
So can we do the swap on the same edge?
Can you?
I don't think we can.
Why?
We already checked it once.
Well, it could form a different path now, right? So now that you've changed the graph a little bit, now maybe there's somebody else who's a better path. Yeah.
Seems like worst case you could come up with every possible combination.
Yeah, so it turns out if you do, so you can actually have exponential running times if you are not clever. Okay, so and actually, yeah, so there's this could end up, could take exponential times if we are careless. So, but very often you can prove that it does not take exponential time because every time we improve by a reasonable amount. Okay, so that's the standard way of showing that the running time is small. Okay, so you show that each time we improve, by a reasonable amount. Okay, so if you look at the objective value, so suppose I look at the matching example, okay, so this is what we did. So every time, if you think of these numbers as integers, then every time I make a swap, I make a swap only if I strictly improve, which means that my improvement is at least 1, right? So if your total cost was bounded, then that gives you a natural bound on the number of swaps you need. Because every time you at least improve your cost by 1 and so on. This is not always possible. Okay, so in fact, there's this whole complexity class called PLS about can you always ensure that you have that local search terminates fast and things like this. Okay, so this is something that we don't know if this can be done for all problems. Okay, because typically you don't have any control, like even on your matching example, you don't have any control on the total, about the fact that they are integers or about the fact that the sum of those integers is bounded. Right? So for this reason, you could end up actually in exponential time. Any questions? So yeah, this is something, if you guys are interested, you can try to come up with an example, and even for the matching, where this actually takes exponential time. And then you will realize what does it mean to say exponential time. It's exponential time in the amount of space you need to write down the instance. Okay. So yeah, let me not dwell on this, but let me just say that with local search, a common problem is the running time. Okay. So you can't often guarantee that you'll make significant progress. So, alright, let's get to that. So these other notions you will understand once you do other parts of the course. So let me not dwell on that here. Okay, so what's next? So the next thing is optimization. Okay, so here I wanted to just have a very high level overview of optimization. Just to say that this is the other place in which local search shows up a lot, which is you have a multivariate function. So you have some function f of x1, x2 up to some xn, and this is like a high dimensional space. Okay, and this is some complicated function that looks like this, and you want to find its maximum or something. And solving these kind of problems is very hard, okay, typically, if the function is not convex or anything. So what people often do is essentially local search. So what you do is you start with some feasible point and then you move in a direction where your value improves. Okay. And it's called hill climbing or various names for these things. Okay, so yeah, move in a direction where value improves. Okay, so I lost this slide because PowerPoint just decided to stop. But okay, so yeah. Okay, so you have a function like this. You always move in a direction where your function value improves, right? So that's what you try to do. Function f of x1 x2. Okay. And this is the most common way in which you solve optimization problems in learning. Okay, so you phrase it as some kind of an optimization problem, like you'll have some parameters that you would want to learn, some classifier or something like this, and you just phrase it as an optimization problem, solve it by local search. Okay, so machine learning, people don't even think about whether you're finding the optimum and so on, typically. Okay. So only recently people have started to think about questions like that. Okay. So that's one thing I wanted to say. Okay, and the most common algorithm here is what is called gradient descent. Okay. So anyone here who has, how many of you have seen gradient descent before in some form? Oh, was it covered in the ML class?
Yes.
Oh, okay, good. So then I don't have to do it much, but all I have to say is that the gradient is a direction in which the function value improves. Okay, so it's so if you want to minimize your function, going in the opposite direction is always good. Okay, so that's why it's called gradient descent, because you want to descend to the minimum of the function. Okay, and so this is one of the most common things. So now that you've seen it, so when does gradient descent not work? Yeah, okay. So I've got many answers, but all of which amount to the same thing. So essentially, things don't work if you have multiple solutions like this. Okay, so if you have values like this, I'm trying to minimize the function. Then once I'm here, my gradient is 0, so I'm kind of stuck there. Okay, so that's the usual case in which gradient descent does not work. So what we want is, so it works for things like convex optimization, where you know that if the gradient is 0, then we are at optimum. And this is true only for convex, but yeah, this is definitely true for convex functions. Okay, so that's so that's what it is. So this is what I was saying initially also, that in some sense local search works only in problems where local optimum is roughly the global optimum. And in the previous examples that we saw, we tried to prove that local optimum is roughly equal to the global optimum. Okay, and that's why things worked out. But people use this all the time for non-convex optimization also, which again you must have seen in machine learning, right? So your function will be non-convex. Maybe you have like a neural network or something where the loss function is extremely non-convex. But people still use gradient descent. Okay. So in practice, people use it all the time. It's used for non-convex functions as well. But it's important to note that you could end up with local locking. So that's so I wanted to make 2 points here, that sometimes you could just end up here and not make progress. Okay, and the other thing is that there are interesting classes of problems which are not convex, but still local search works. Okay, because convexity is, if you think about it, it's a very strong requirement, right? It's like saying the function looks like a bowl, but your function could look pretty complicated. It could look like this. This is not convex. But still you have the property that every local optimum is a global optimum. Okay. So this is one thing you should remember about local search, that what you really need is this condition, local optimum being global optimum. Okay, so you don't necessarily need convexity. Has anyone seen examples of optimization problems where this kind of a situation happens, where local optimum is global optimum, but it's not convex? I'm sure all of you have seen it, but you probably didn't realize. Sorry?
What did you say? Local is?
Local optimum implies that it's also a global optimum.
So it's not convex.
But the function is not.
The sine function?
The what?
The sine function with every local optimum?
Yeah, no, definitely yes. But no, I meant like a standard optimization problem that you might have seen, where this sort of a behavior happens, where the function is not convex. So yeah, let me write it and then you will realize it. Okay, so if you have eigenvalue problems where you have where your function is this divided by this. Okay, so this is what's called the spectral norm of a matrix, or the top eigenvalue of a matrix. Okay, so this function itself is not convex, but it has the nice property that local optimum are a global optimum. This is why things like power method and so on work for this problem. Okay, so you can still move around locally and get it all. Okay, so this is just in case you're interested in these things. Okay. So that's why it's important to remember this. So as long as you have this, local search is decent. Alright. Yeah, so these are other heuristics, so let me not spend much time on this. Okay, so next week we'll start looking at graphs. Okay, so many of you, it will be more of a review of things, but I'll try to make it somewhat interesting for those of you who've seen these things before. Okay, so we'll look at shortest paths, all pair shortest path, things like this. So this is all part of standard undergrad courses, so I'll put up some references. Try to read beforehand if you haven't seen these before. Okay, so that we'll go at a relatively faster pace. And yeah, before you guys go, so can you guys think of local search algorithm for shortest paths? You have a path to try to improve it. Any suggestions? So you'll face difficulties, mainly because there are some problems in which you have a path, you have a totally different path, right? So there's no way you can locally improve these things without doing a pretty long search. Okay, so you have to search for paths of this like 3 or something. So this is the usual. This is another issue you've got to keep in mind. That yeah.
Either way more showing up before thought in that way, you sort of have
Yeah, I know what you're talking about, but not quite, because you should think of having a pair, you have an equivalent pair. Then you will keep making improvements. But if you just have you and
well, you can sort of
Because what you will end up finding is that Melvin Ford essentially adds this edge. I mean, even if this was a long path, it will end up adding this edge. And then this would just be a length 2 path. That's why you will define it. Alright, let's start.